So this is going to be our last installment in the purely Pythagorean Theorem aspect of the trigonometry lessons. Today we're going to be learning about special right triangles. Okay, so there's going to be two different types of special right triangles that are going to be derived from pretty familiar shapes. They are going to contain angles in them that are going to be relevant to our further study of trigonometry, and so this is the reason we're covering them. They're really simple, and we're going to use the Pythagorean theorem to derive all the facts that we want about them. So I'm going to erase this, and we're going to get started. So the first shape we're going to analyze is an equilateral triangle. So a triangle that has all three sides the same, and sort of also has the forced aspect that all of its angles are the same. Right? That's not true for any other type of polygon. Triangles are special in that way, that if you make the angles all the same, it forces all the sides to be the same, and if you force all the sides to be the same, it makes all the angles be the same. So they're both true at the same time. But we're not actually going to focus on this shape, we're actually going to focus on half of it. But before I do that, let's analyze something. So all three sides are the same. Now we know that all three angles in a triangle have to add up to 180 degrees. So if there's three congruent angles, then each of them has to be 60 degrees, right? All three of them have to be 60 degrees. What we're going to do is we're not going to actually look at the whole triangle, we're going to look at half of it. So we're going to look at half of the triangle. And this is important because now we have a right triangle. So all I did was drop an altitude or a vertical line from the vertex, from the top vertex to the middle of the other side. And now that I've bisected this angle up here, now that this is 90 degrees and this is 60 degrees, that must mean that this is a 30-degree angle up here. So we have what is called a 30, 60, 90 right triangle. So this is one of the special right triangles. Now, because this was half the side of the regular equilateral triangle, if we call this x, then we know that because the hypotenuse of this right triangle is still just the original side of the equilateral triangle, that this must be 2 times x. Because x is half the side of the regular triangle, the full side of the regular triangle must therefore be 2x. And so the question remains is, what is the value of this leg right here in terms of x? Well, this shouldn't be too hard. We have the Pythagorean theorem, right? So let's call this b, just to give it a name, and we're going to solve for b in terms of x. Well, what does the Pythagorean theorem tell us about right triangles? It tells us that if we take both legs and we square them, then add them together, we get the hypotenuse squared. In other words, x squared plus b squared equals 2x squared, right? So this is our formula, and now what we're going to do is we're just going to simply solve for b in terms of x. So this can be, simplified. We can distribute the power, and we get x squared plus b squared equals, now we have to distribute the power, so 2 squared is 4, and then there's x squared, so this is equal to 4x squared. Okay? So now we're just going to combine like terms, right? X squared moves over to here, and we can subtract it from both sides, and we get that b squared is equal to 3x squared. Because there's 4 of them over here, we're taking one of them away, so we're left with 3. Now to solve for b, all we have to do is take the square root of both sides. So we get that b is equal to the square root of 3x squared. The square root of x squared is just x, and the square root of 3 is just the square root of 3, which makes b equal to x times the square root of 3. So this is our scale factor. So given that one of the legs of the right triangle is x, and that the hypotenuse is twice that leg, we know that the third one has to be x times the square root of 3. So this is a little cluttered, I'm going to erase that, and so we can see that. We've solved it here. To give you some perspective about how big that is, the square root of 3 is about 1.73. It's irrational, so you're not going to get a fractional value for it, but it's around that size, right? And that should make sense. It's shorter than the hypotenuse, which is 2 times the smaller leg, so it should be something between 1 and 2 times the length of the shortest leg, and that's what it is right there. The great thing about this is that this allows us to derive some interesting values, right? Let's bring it back to trigonometry for a second, because what can we do now? We have a triangle with angles that we know and sides that we know the ratios of, which means we can do all of our trigonometric values. So we can just do a couple. I'm just going to show you the signs of all of these angles, and you'll see that we can actually figure out all the others pretty simply just from that information. So if we take a look at 60 degrees, we see that the opposite side is x times the square root of 3, and the hypotenuse is 2 times x. So that should lead us to believe that the sine of 60 degrees is equal to x times the square root of 3 over 2 times x. Right? But remember, the scale factor that these sides are being multiplied by doesn't actually matter. If you recall from the discussion about triples of right triangles, take the 3, 4, 5 right triangle and the 6, 8, 10 right triangle. The latter is just a scaled up version of the former, and all of the angles inside either of them are exactly the same because they're similar shapes. So all of the trigonometric functions give you the same values. It actually doesn't matter the size, because take a look what happens. The x's cancel. X divided by x is 1, assuming x isn't 0, which of course it isn't because it's a length of a right triangle, and therefore we've just discovered that the sine of 60 degrees is root 3 over 2. Is the square root of 3 divided by 2. Okay? So let's keep that in mind. And now if we take a look from a different perspective, what is the sine of 30 degrees? Well, the sine of 30 degrees is going to be the side opposite it divided by the hypotenuse. So the sine of 30 degrees is equal to x divided by 2x. So that's x divided by 2x. But of course, the x's cancel once again, and the fact that the triangle was any sort of size doesn't matter. What matters is the ratio of the sides. And we end up with the cool fact that the sine of 30 degrees is 1/2. So we can derive that just from figuring out this remaining side of the 30, 60, 90 right triangle. So we've got one more triangle to take a look at. So let's go ahead and do that. This time we're not going to be analyzing an equilateral triangle. We're going to be analyzing an equilateral quadrilateral with 90-degree angles in it, also known as the square. Right? All of those are 90 degrees, and every side is the same length. So it's a particularly symmetric and nice shape. And what we're going to do to get the triangle that we want to analyze, we're simply going to cut that in half, like that. So we're going to slice a diagonal right up the middle of the square, and we're simply going to not consider the other half because it's just a copy of the triangle we're going to analyze. Because it started off as a square, we know that both of these legs are in fact the same length. And there are two things we can deduce about the angles. Well, there's one thing we can deduce about these angles here, two ways to do it. One, two of the sides of the triangle are the same. By the isosceles triangle theorem, we know that the opposite angles are actually both the same. We could also see that we were sort of bisecting both angles just by drawing that diagonal. Now, because this is a 90-degree angle, and all three angles inside of a right triangle must add up to 180 degrees, and these two are the same, these two must both be 45 degrees. Right? Together they add up to 90, plus this gives us 180. So we know that these are the same angle. And of course, we want to find out what the hypotenuse C is in terms of our side length x. And this isn't going to be too hard because, again, we have the Pythagorean theorem for that. So we know that x squared plus x squared equals c squared. This is even easier than the previous one because all we have to do is combine like terms right here. And of course we can see that this is equal to 2 times x squared just by combining those two like terms. And now to solve for c in terms of x, we simply take the square root of both sides and we arrive at the conclusion that c is equal to the square root of 2x squared. And the square root of x squared is just x. The square root of 2 is also irrational, just like the square root of 3, so it has to stay. And we find out that c, in terms of x, is just x times the square root of 2. Okay, so we've discovered that x times the square root of 2 is the hypotenuse of an isosceles right triangle with legs of length x. And again, to give some perspective, the square root of 2, not a rational number, but just to sort of let you know how much you're scaling up by, it is about 1.41. But it's irrational, right? So maybe I'll do a proof on why it's irrational one day. If not, there's plenty of proofs on YouTube that are all more or less the same. So that's the number that we're multiplying by to get this. And so we can do the same thing that we did last time and we can discover some trigonometric values. Notice how there's only one value for us to look at here because both angles are the same though. So I'm going to erase this now that we've derived the length of the third side. And we're going to ask ourselves, what is the sine of 45 degrees? Well, the sine of 45 degrees is equal to x divided by x times the square root of 2. So x over x times the square root of 2. And once again, because x is not 0, right, it's some length right here, we can just cancel these. And we see again that the size of the triangle doesn't actually matter, and that it only matters is the ratio of the sides, and we come to the conclusion that it must be equal to 1 divided by the square root of 2. Now there's something that is taught in geometry classes called rationalizing the denominator, and it's called that because the number in the denominator right now is an irrational number. Now there's nothing mathematically wrong with saying 1 divided by the square root of 2. The square root of 2 is not 0, so you can divide by it all day long. There's nothing wrong with this number. It's about 0.707, I think. The issue is the concept of saying take something that you have, one thing, and cut it up into the square root of 2 pieces. That's pretty hard to conceptualize. How many pieces is that? So what makes it slightly easier is we're not going to change the value of this number, we're going to change it sort of cosmetically, right? We're going to multiply the top and the bottom by the square root of 2, like that. But the square root of 2 divided by the square root of 2 is just 1. So this doesn't change the value of the fraction, right? It's just multiplying something by 1 so as to make it cosmetically different. And the cool thing is in the top we just get the square root of 2. And then in the bottom we have the square root of 2 times the square root of 2, which is the same thing as the square root of 2 squared, which by definition gives us 2. So the sine of 45 degrees is equal to the square root of 2 over 2. I don't have to do the sine of 45 degrees again because it's the same thing, right? We're going to get x over x root 2, and we're going to arrive at the same answer. So now we've derived all three of those values. We've derived the sine of 30 degrees, 45 degrees, and 60 degrees. And so we're going to be able to derive all other trigonometric values just from those things alone. And so that's enough of special right triangles today. I'm going to fill you in on the final proof that I have memorized of the Pythagorean Theorem, my personal favorite proof. Here we go. So my personal favorite proof of the Pythagorean Theorem comes from essentially similar triangles and sort of treating it like a puzzle, like a physical jigsaw puzzle. And it's a beautiful proof. So let's take a look. So we're going to start with a general right triangle with side lengths A, B, and C. And what we're going to do is we're going to scale this triangle up by whatever A is. We're just going to multiply every side by A. Okay? A is not 0, so it's not like it's going to make our triangle disappear. We're just going to imagine A were 2. We would just be doubling every side. Whatever A is, we're just going to multiply by that. So we're going to end up with a new triangle. I'll give us a different color, just to highlight. So we're going to scale everything up by A, and just for the sake of consistency, we're just going to assume that all A, B, and C are bigger than 1, so the triangles are going to get bigger. But in principle, A, B, and C could be anything that makes a right triangle, even if those numbers are less than 1. And the proof will still work. For the sake of consistency, we're just going to pretend that they're all bigger than 1, so every scale I'm going to do is going to make the triangle bigger. That has nothing to do with the inherent truth of the proof. So if we scale everything up by A, then this side length becomes A times A, which is A squared, right? This is our right angle. This side becomes A times B, and this side becomes A times C. There's actually one more detail that I want to highlight before we go on, because it's actually rather important. We need to focus on these angles, right? We know that this is 90 degrees, but we don't have a fixed value for these angles. We know that together, though, they must add up to 90 degrees, because the sum of the angles inside of a triangle must always be 180. This is already 90 degrees, so the other two have to add up to 90, even if we don't know what they are. So I'm just going to give them names, and I'll write down that fact. So the angle across from A, we're going to give it the value alpha. Okay? The Greek letter A, almost. And across from B, we're going to do the same idea. We're going to call it beta. Right? Those are just the names of these angles, alpha and beta. Now, we don't know what alpha and beta are individually, but we know that alpha plus beta equals 90 degrees. They are the non-right angles in a right triangle, so they must add up to 90 degrees. And that's going to be important. So I'm going to keep track of which ones are alpha and beta in every triangle, because remember, these are all going to be similar triangles. So the angles aren't changing, only the size of the triangle. So this angle is alpha, this angle is beta. Same exact values as here. So these are both beta and these are both alpha. The triangles are different sizes, but the angles are the same, right? They still share the right angle, and they still share beta and alpha. Okay? Alpha plus beta equals 90 degrees. And I want to keep that fact tucked away just in case we need to be reminded. And now actually we're going to take this triangle, we're going to set it aside, the scaled up by A triangle that we just did, because we're going to do it again. Except this time we're going to scale this triangle up by B. So we're going to multiply every side by B. It's going to be a similar triangle. We're just setting this one aside. And now we're going to scale up our original triangle by B. I'm going to redraw it in blue again. We're going to scale this triangle up by B. and we end up with a times b times b, or b squared, and c times b, or bc. And again, to highlight, all of the angles are exactly the same. So this is still alpha, and this is still beta, right? And still, alpha plus beta equals 90 degrees. Even though we don't know what alpha is and what beta is, we know that their sum has to be 90 degrees. It just has to be, because it's a right triangle, and their right angle already takes up 90 degrees. I think you can probably guess what we're going to do now. We're going to set this triangle aside, and we're going to scale up the original triangle by c. Okay, so there's our triangle tucked away. You can't really see all the details, but that's not really important. So what I'm going to do is I'm going to take our original triangle, and I'm going to scale it up by c. So it's going to be the biggest one. C is the biggest number because it's the hypotenuse, and I'm going to scale it up by c. And I'm going to draw it in a particular way. I'm going to draw it almost laying on its hypotenuse. So the right angle is sort of sticking up into the air. So I'm going to draw it like this. So there's our right angle. And now I'm just assuming that A is the shortest side. It really doesn't matter if A or B is bigger than the other. What matters is that C is the hypotenuse. Because I'm scaling everything up by C, this is now going to be A times C. The other leg is now going to be B times C. And this side length, because I've scaled up by C, is now going to be C times C, or C squared. Right? And now the important bit is to highlight that this is the angle beta, and this is the angle alpha. Now, I'm going to do the last step of the proof. Notice something. This length AC is the same as this length AC, right? They're the same numbers. A times C must give the same numbers. So actually, I'm going to write this on the inside of the triangle. And notice, alpha is here and beta is down here. If I tuck alpha right up next to beta, I know that I'm going to get a right angle because they add up to 90 degrees. So if I take this and align it here, while matching up this AC length with this AC length, sort of by flipping it around and just sort of tucking it in the spot, I'm going to end up with this. So this is still AC, and this angle, alpha, has been tucked down here. So we actually end up with a right angle, because alpha plus beta is 90 degrees. So alpha and beta are both tucked in there. This side length is A squared up here, and this side length is AB right here. Okay? Now we're going to do the exact same thing with the other triangle. Notice we have a length BC right here for this hypotenuse of the other triangle. It's the same as this BC right here. So we're going to take this BC and snuggle it right here, align it with this BC. Notice that this is the angle alpha, so we need the angle beta to be tucked right in here with this one. And notice we've got AB and AB. So this is important, these things that are coming together. So we're going to sort of take this and flip it around so that BC lines up with BC and beta goes with alpha. And it's going to look like this. So this is now beta tucked in here as well, which means this also creates a right angle because alpha plus beta equals 90 degrees. This is our 90-degree angle. And what's this length here? This is B squared, and this is AB. Right? So we have B squared right here, and we have AB on this side. But now take a look what we've got. We've got a quadrilateral with 4 right angles in it, which makes this a rectangle, which means that opposite sides are the same, right? And that's clearly stated here. AB is, of course, equal to AB. But look what else that reveals. It reveals that this length A squared plus this length B squared is equal to C squared. Isn't that wonderful? A squared plus B squared equals C squared. It's my favorite proof of the Pythagorean theorem. The reason that it's my favorite is because you could literally build this. You could make these triangles, right? You could do a 3, 4, 5 triangle, scale everything up by 3, make that triangle, scale everything up by 4 and make that triangle, scale everything up by 5 and make this triangle, and then you could put them together and you will see that it works. It will work. It will physically work, and you can make it tangible, which I think is just absolutely wonderful. And so that will conclude our video for today. Next video we will be moving on to the unit circle and applying those special angles that we learned and figuring out all of those trigonometric values. Thanks for watching.